Now let's take a look at some of the properties and how they relate to our theory. So the first property we're going to look at is atomic radius. And when we sketched our graph, we had the general shape, and what we did was we labeled our peaks and our valleys. And what we can see is that for my atomic radius, the elements in each period, or the period that, the elements in each period that have the largest radius are those that are found in group 1. Any elements in each period that have the smallest radius are in group 18. And we can see that as we go across a period, my radius decreases. And we can see as I go down a group, my atomic radius increases. Okay. Well, what we can see is that within a group, since each period represents an energy level, this would cause an increased distance between my nucleus and my valence electrons. And so this is what accounts for increase in size. Whereas within a period, as I move from left to right, I'm adding electrons to the same energy level, but I'm keeping my number of core electrons the same. So this results in my ENC value increasing, which would therefore increase my force of attraction. So as a result, this atom, its valence electrons, feels a slightly greater force of attraction to the nucleus than the valence electrons of this atom. So as a result, what we see is that these valence electrons get pulled in slightly more than these valence electrons. And this trend occurs across the period. Okay, first ionization energy. This is another property that we looked at, and it's the energy associated with the removal of an electron. And we can see our general formula here. Again, when we drew our graph, we saw this. We saw that within a period, the elements with the highest first ionization are my group 18. The ones with the lowest first ionization are group 1. As I moved across a period from left to right, my first ionization increased. And as I moved down a group, my first ionization decreased. So within a group, what happens is that we increase our distance to the valence electrons. So period 1 has a distance value of 1. Period 2 has a distance value of 2. Period 3 has a distance value of 3. Now they all have the same ENC value, because as we stated, all the elements in a group have the same ENC values. So ENC is constant. This has an ENC value of 1. This has an ENC value of 1. And this has an ENC value of 1. But because the distance increases, this causes our force of attraction to decrease. So this atom here would have a greater force of attraction to its valence electron than the valence electron of this atom. So as a result, since the force of attraction that this valence electron feels is lower than the force of attraction this valence electron feels, it's easier to take this electron away. And this is why my first ionization energy decreases down a group. When we look across a period, what we find is that my first ionization increases. And because as we go across a period, again, we increase our ENC value. So here I have an ENC value of 2. Here I have an ENC value of 3. Here I have an ENC value of 6. And here I have an ENC value of 7. So since my ENC values are increasing, but my distance is the same, 2, 2, 2, 2, that means that the attraction that this valence electron feels is greater than the attraction this valence electron feels to the nucleus. And so it'll take more energy to remove this electron than the first atom on the left. And that's why my first ionization energy increases across the period. Okay, let's look at electron affinity. Electron affinity is a tricky one to look at because we define it as our energy change. And our energy change is not always the same. Sometimes it costs energy, and sometimes an atom will release energy when I add an electron to it. Well, this makes sense intuitively because metal atoms which don't want an extra electron, we're going to have to make them take it. So it's going to cost energy. Whereas a non-metal atom which wants an electron, because it might fill its valence energy level, will give me energy back because it enters a stable state. Okay, and so as a result, our graph isn't quite as clear-cut as it is for the other trends. But what we can see is that our group 18 costs the most to add an electron to, well, because I would be adding an extra energy level. My group 18 requires the least energy, and in fact, fluorine gives off lots of energy, and we have changing energy down the group. If we look at our theory, what we see is as we go down a group, it costs more energy. And the reason it costs more energy as I go down a group is because my distance increases. And so since there's a less of a force of attraction for this electron than to this one, or to one that I add in this energy level, or one I add in this energy level, then what that means is I'm going to have to provide energy to get it to take it. And so the further the distance, the more energy I'll have to add. So therefore, this would require lots of energy. This would require only a little bit. Within a period, again, it's due to our differences in our E and C value. This atom here, since its valence energy level is not full and it has a low force of attraction, it may cost me energy to give it an electron. Whereas this element over here, where the addition of a valence electron would fill its valence energy level, it would probably give off energy. And so as a result, I have a decreased cost. So it costs more energy here, it costs less energy here. Okay? It requires more energy, and my energy requirement decreases as I go across the period. It's due to an increased force of attraction as a result of a higher E and C value as I move across the period. Our last property or trend that we looked at with the periodic table is the electronegativity. And this looks at how an atom attracts the electrons in a pair. So if two atoms came together and formed a bond, those electrons that are in that bond can be attracted to the nucleus of the two atoms involved, either equally or unequally. And so my electronegativity is a way for me to evaluate the degree to which they're attracted. So what we see when we look at this is that in general, my group, as I go down a group, my electronegativity decreases. As I go down a group, electronegativity decreases. And as I go across a period, my electronegativity increases. We can also see that fluorine, by our scale, is given the highest value, and all the other elements are standardized against fluorine. This is why fluorine has the highest value. And francium has our lowest value. Okay. Well, like our other trends within a group, the difference is due to distance. As I go down my group, I increase the distance to my valence electrons, so I have a lower force of attraction. So therefore, since my force of attraction to the valence electron is lower, then my force of attraction to a bonding pair electron, so I'm going to have another atom come here and share, and then it would share the two electrons, that attraction will also be lower. Whereas if my distance is smaller and I have another atom come and now they're going to share two electrons, since the d is smaller, it's going to have a higher force of attraction. It's going to be able to attract those bonding pair electrons more. And then within a period, just like our other trends, the trend is due to a change in our E and C value. If I have a low E and C value, I'm going to have a lower force of attraction, so I'm going to be less likely to attract my bonding pair. If I have a higher E and C value, I'm going to have a higher force of attraction. I'm more likely to attract those bonding pair electrons.